Hi, I'm Danica Krista from the Department of Artificial Intelligence and Machine Learning. Here I'm going to present about the mini project title, which is Polypharmacy Side Effect Risk Predictor. So the problem statement here, while the adverse drug reaction caused by drug-drug interaction remains a major clinical challenge, while using classical machine learning struggles with extremely high dimensional molecular data and non-linear biochemical relationship, a manual evaluation of drug risk is low, error-prone, and not scalable. Our objective is to design a hybrid quantum model for predicting the low, moderate, high interaction risk by using the SMILE encoded drug pairs. So the scope of the project. So we develop a hybrid quantum classical machine model for predicting the interaction risk between drug pairs. We utilize the molecular fingerprints, which is the Morgan fingerprints, PCA compression, and variational quantum classifier for predicting the risk. So the audience here is the medical professionals, pharmacologists, healthcare researchers, and the clinical decision support teams. So we deliver the fully trained and evaluated hybrid quantum model for predicting the low, moderate, high risk levels, which is a user-friendly interface here we have developed. So the inclusions are the drug pair dataset for training. We convert the drug names into smiles, which is further converted into the Morgan fingerprints. We use PCA for dimensionality reduction. So the training baseline is to use classical models and hybrid models to build a prediction interface for risk scoring. So we use the publicly available dataset, which is the drug pairs and associated with side effects. We convert the drug names to smiles using PubChem and generate Morgan fingerprints. We apply PCA for dimensionality reduction. We apply the pre-processing steps for cleaning and label encoding. So the first step is data set acquisition, which is drug-drug pairs and the side effect labels were collected from the Kindle and prepared for supervised learning. So the data pre-processing steps. We convert the data names into smiles. Morgan fingerprints are generated. So we encode the labels and use PCA to reduce 2040 dimensionality vectors into quantum compatible features. We use hybrid quantum model to build the angle embedding and strongly entangling layers, followed by the classical linear head for risk classification. We have developed a web app for which is a user-friendly interface which accepts the drug input and display interaction risk prediction generated by the trained models. So the architecture flow diagram is we take the drug data set, we use the pre-processing feature extraction, we use quantum encoding, we train the model to predict the risk levels, which is the low, moderate, high, which is delivered to a user-friendly development to the doctors. So the algorithm used are Morgan fingerprint algorithms, which is used to convert the molecular structure represented as smiles into fixed-length numerical feature vectors, which capture structural and tropical information of molecules including circular substructure hashing, enables effective representation of chemical properties required for interaction prediction. Fingerprints of two drugs are concatenated to model pairwise interaction. We use PCA to reduce the high-dimensional fingerprint vectors, which is 2048 features, into lower dimensional representation. We use variational quantum classifier, which is implemented by using the penny lane. Uses Angler embedded to encode classical features into quantum states. Strongly entangled layers from a parameterized quantum circuit for learning complex patterns. We use random forest classifier as a baseline model. The software used are PennyLane, which is a hybrid quantum classical model development. We use PyTorch for classical encoding, optimizer, and training pipeline. We use Scikit-learn for implementing PCA random forest baseline evaluation matrix. We use NumPy and Pandas for data preprocessing and storage. So the development environment is by using Python 3.9 plus versions. It can be implemented by using Jupyter Notebook for experimentation, VS Code for development, and GitHub for version control. So we have we use pre-processing techniques, which is used to convert smiles into Morgan fingerprints by using this code. We have used a quantum circuit definition to control the complex patterns of the data, which can be superposition and entanglement. We have used hybrid quantum classical training to convert the quantum model. We have used this technique for improving the model of a quantum model by using a classical optimizer. So the output or the user interface, here we have to give two drug names, which is converted into smiles. So this smiles gives a risk level using hybrid quantum classical machine learning model, which gives the low, high, moderate risk level prediction. So the results here, by using the hybrid quantum machine learning model, the accuracy here we have got is 34.12. The F1 score is 20.35. So in conclusion, we have explored the hybrid classical approach for predicting drug-drug interaction risk using molecular fingerprints and variational quantum circuits. The experimental results show that we have proposed a model achieved